So Kirill did his study in Nizhny Novgorod, and then worked for his PhD in Germany at Karlsruhe Institute of Technology, where he graduated, I believe, like 5 years ago or 6 years ago already. And he's working now as a staff member of Walther-Meißner-Institute in Bavarian, Munich, where he leads several projects on quantum communication with quantum microwaves. And this is actually the subject of his talk. So Kirill, thanks for your agreement to give a presentation at the school. And yeah, take the word and share your screen if you are ready.
Thank you, Alexei, for your introduction. I hope you can hear me well. So let me first of all go in my presentation mode, and then I will try to share my presentation with you. Yes, so I'm going to talk about this continuous variable quantum information processing, and I will also try to establish enough of links between this topic and superconducting circuits. So let me begin with showing you the outline of my lecture. So I will spend roughly the first 30 minutes to make a proper introduction into this topic of continuous variable quantum information processing by introducing the appropriate Gaussian states, such as the squeezed vacuum states, and talking about some fundamentals of quantum information processing with continuous variables. Then I'm going to continue by talking about continuous variable microwave information processing, and I will talk about their properties. Specifically, I will talk about how we can generate them by using superconducting devices, such as the Josephson parametric amplifiers, and how we can measure them and what kind of interesting physics can be achieved with them, such as the two-mode entanglement. Then I'm going to spend the rest of my talk by talking about some of our results in the field of microwave quantum communication, namely remote state preparation or quantum teleportation. And this is something we can do in the microwave regime nowadays. And then I will finalize by actually making a short outlook about some near and far term future of this information process. So let us get started with this introduction. So first of all, what we already learned from the lectures yesterday and today is actually our beloved and very well-known discrete variables. This is something which is typically nowadays taught everywhere in the form of quantum bits. And we know that in principle, quantum bit, in contrast to the classical bit, it can be also in the superposition states. And this is something which we can actually use for the purpose of a quantum computation, and that's the root of its power. Essentially, the ability of quantum bits to be in the superposition and then entangled states. However, there is an alternative way to encode information in general. We can use other operators, such as, for example, position operators, which might have a continuous valued eigenspectrum and corresponding spectrum of eigenstates. And this can be represented, for example, by taking a very simple example of a propagating electromagnetic wave, which is routinely described by its amplitude and phase phi. As we already have heard today, actually phase operator phi is somewhat problematic. Its definition has problems in quantum mechanics. This is why for our description, we will most often use actually different operators, the so-called electromagnetic quadratures P and Q, because they don't have the associated difficulties. And just to introduce basically how we can connect to those quadratures and what does it mean in the language of quantum mechanics, I will introduce a very basic quantization of the electromagnetic field, which one can find in many quantum optics books, such as the famous Walther-Milman textbook. So here I apologized for basically bringing up this very general topic, but maybe for some students it might be useful to refresh their knowledge on this in this area and how we can actually quantize the Maxwell equations. In principle, the path towards quantization is very straightforward. We typically start with source-free Maxwell equations, which are shown here, and then we exploit a very particular Coulomb gauge in order to arrive to the wave equation in terms of the vector potential A, as it is shown and highlighted here. The next step is to solve this equation in the classical regime by introducing right and left propagating components of the wave vector, as it is shown here, for the positive frequencies. We don't consider negative frequencies here. Then we typically restrict our field to a finite volume, even though it can be very large. And then we write down the corresponding solution in terms of the Fourier coefficients Ck, which are constant, and corresponding vector mode functions Uk, which also must satisfy a set of conditions such as wave equations, transversality conditions, and orthogonality conditions, which are pretty very well known if you just study from classical electrodynamics. And of course, those conditions also depend on the boundary conditions. And this is what we should also remember, that there are different types of boundary conditions, such as periodic or reflecting. And here we consider, for example, a specific example of a cubic volume with a side length L. And then the corresponding mode functions can be written as it is shown here. And then we make an important simplification that we consider, since we are going to consider mainly propagating microwave waves, which are propagating in symmetric waveguides, then we typically do not have to consider any polarization. And we can essentially get rid of various polarizations and simplify our description by simply considering superposition of plane waves. And then we do the key step. We essentially replace our classical Fourier amplitudes with the corresponding ladder operators, or creation and annihilation operators, which must follow the bosonic commutation relations which are shown here. This is essentially the key of our quantization procedure. And then we arrive basically at the corresponding formula for the vector potential, which is already quantized, and each mode is quantized here. Then respectively, we can rewrite it in terms of the electrical field intensity, as it is shown by the corresponding series, or already also in this quantized form with the corresponding ladder operators. And then, based on this description, we can rewrite and introduce the corresponding Hamiltonian, which is introduced as a sum of independent modes, K modes, which are defined essentially as a sum of H omega times A dagger A plus 1/2. And this is, of course, our beloved vacuum fluctuations. The important result of this rather well-known procedure is that now we can treat the corresponding quantum states with the corresponding pure wave functions psi k independently for each of these modes with the different frequency omega k. And this will be important for us. What we also have to remember then is that when talking about classical single mode electromagnetic waves, such as described by the corresponding oscillating formula, we can also introduce the equivalent description of those waves with the field quadratures Q and P, which can be related to the corresponding amplitude and phases with these simple and very well-known formulas. We also have to pay attention that in engineering, those quadratures are sometimes called P, and P is called I. So these are I and Q quadratures, such as, for example, when we are using IQ mixers, but not P and Q mixers, but this is just equation of notation. Those field quadratures are in principle analogous to momentum and position in mechanics, and one can establish a very simple relationship between them, as we know from the conventional quantum mechanics course. Next, those quadratures are also subject to the corresponding commutation relation, and we can write down the corresponding uncertainty relation for their variances as it results from this Heisenberg uncertainty relation. Then, as a result of all these operations and procedures, we can establish a very useful duality for describing our propagating modes. That from one hand side, we can treat our single mode quantum fields via the ladder operators, which provides us with a very useful discrete variable basis, where the eigenstates of this basis are essentially the Fock states or number states, which corresponds to single photon states, such as, for example, single photon state 1. On contrary, we can also rewrite it in terms of these quadratures, and then our Hamiltonian will simply look as p squared plus q squared, where p and q is our quadrature operators, which provides us with a different continuous variable basis, and the set of the corresponding eigenstates for either p and q also form a certain basis. And the natural eigenstates for this basis are the so-called Gaussian states, which we are going to discuss, which come in different sorts, such as the coherent, squeezed, or thermal states. What is important for us to remember, that in principle, any quantum state can be expressed either in the continuous variable or discrete variable basis. And respectively, any quantum task, such as quantum information task or quantum simulation task or communication, sensing, those different tasks can be also conveniently expressed in continuous or discrete variable basis. Nevertheless, a particular basis might be more or less suitable for solving a particular problem, as we are going to see by considering specific examples. But before going to consider those examples and states, we have to say something about how we are going actually to describe these states. Because the situation is not always very easy, because as long as we take kind of our ideal quantum states and couple them even a little bit to environment, we go into the mixed states, which cannot be described by pure wave functions. So we have to use the density matrix description, which we also in principle know very well, so that we expect our quantum state to be in the classical superposition of various pure states with the corresponding various classical probability coefficients and corresponding normalization condition. The problem of the density matrix approach that these entries in principle might be complex in general, which are not very easy to visualize. This is why we can use a different approach to visualize our quantum states, just to understand experimentally what's going on, is to use the so-called phase space representation of our quantum states, such as the phase space which is spanned by our quadratures Q and P. In this particular situation, when we are talking about classical states or ideal classical states, the situation is very simple. Those states can be described essentially by points, by dots in the phase space, such as it is shown here, in the absence of noise. When we have actually some noise, those states can become, of course, not dots, but some kind of positive distributions with specific variances. Nevertheless, those distributions will be always positively defined. And when we introduce quantum states, the situation changes even further, because we have to remember that even in the absence of any noise, due to the omnipresent quantum noise, due to this Heisenberg uncertainty relation, we will always have some kind of noise, even in the situation when we remove all coherent photons from the consideration, which essentially gives rise to the so-called vacuum state, which is depicted here, basically on this phase space plot. These are the corresponding vacuum variances, which are here. Just this is simply the definition of vacuum variance in a certain normalization. This is why it's given in absolute units. In general, this phase space representation, especially for vacuum states, might also require negative probabilities. And that's the big difference, because negative probabilities you cannot obtain from Maxwell equations, and this is something new. And those negative probabilities are especially known when dealing with Fock states, such as Fock state 1. And the corresponding quasi-probability distribution is usually introduced by the so-called Wigner function, which is depicted at the bottom of our current slide, which is a specific integral over the whole phase space, which is connected to our density matrix. So essentially, when we know our Wigner function, it is equivalent to knowing the density matrix of our quantum state. And this is going to be very important for us during this lecture, because this is how we are going to visualize most of our quantum states, by using the corresponding Wigner functions. But in principle, we can also remember that we can also simplify our situation even more a little bit when talking about quantum states, because most of the states we are going to consider today are the so-called Gaussian quantum states, which are a little bit closer to the classical states, but nevertheless still with many quantum features. Those Gaussian quantum states can be explained and understood by using a little bit simpler formalism, by using the so-called covariance matrix formalism. So let us quickly talk about what it is. This is in principle a natural description of an arbitrary n-mode Gaussian state, which can be given due to its Gaussian nature by statistical moments of these quadratures, such as the first statistical moment is simply the mean displacement vector d, which is introduced as the expectation values of the corresponding quadratures, where we have in principle n modes. And of course, the simplest situation, oh, sorry, I think here there is a typo, this must be P. Of course, this might be Q1, P1, and then Qn and Pn. That's a type. Respectively, we can introduce the second statistical moments, which are given via the covariance matrix sigma, which is the 2n by 2n real symmetric matrix, which is defined based on this displacement vector, but not the mean displacement vector, but the actual one, the operator one, where basically different entries of the covariance matrix are represented by different variances or covariances of the corresponding operators, and therefore it is called the covariance matrix. What is important for us to know is that in the limit of Gaussian states, the corresponding Wigner function of the quantum and arbitrary Gaussian state can be always calculated by knowing the corresponding covariance, the displacement vector. So essentially the knowledge of displacement vector and covariance matrix is equivalent to the full knowledge of density matrix or Wigner function. But of course, this works only in the Gaussian limit. If we go outside of the Gaussian limit, this is no longer true. For example, for the Fock state 1 situation becomes a little bit more complicated. So let us now introduce some fundamental Gaussian quantum states, which we are going to need to understand some basic results for quantum information processing with continuous variables. The first and the most simple of continuous variable Gaussian quantum states is the coherent state, which is generated by applying the so-called displacement operator to vacuum, which corresponds simply by displacing vacuum state along a certain direction in phase space, which is defined by the complex amplitude alpha, as it is shown by this 1/e contour, or this is the corresponding Wigner plot, and this is the 3D Wigner plot, which shows this displaced state. And this is how the corresponding displacement operator looks like. So it's basically a very simple first order, corresponds to first order Hamiltonian. And the corresponding Wigner function is also just a symmetrically displaced Gaussian state. What is important for us to remember is that these coherent states are the most classical quantum states. First of all, they don't generate any entanglement. And second, we can show that in the classical limit, the expectation value of the amplitude for the coherent states can be essentially obtained, and these are the closest, essentially it coincides with the classical description. This picture can be obtained by calculating the corresponding expectation value, as it is shown here, where with A, this is the amplitude operator, which is defined by A plus A dagger divided by 2. And of course, then we have to remember that due to the properties of the coherent states, these coherent states are the eigenstates of the annihilation operator. This is actually was historically the way how these states have been introduced. And then the way to actually obtain this classical limit is relatively simple. I'm just going to sketch it, but I don't go into details of this calculation. So I hope you can do it yourself. And if you have any problems, you can always send these questions to me later. You in principle simply have to go to a certain interaction picture, which means that you have to go from your amplitude operator to the amplitude operator in the interaction picture, which means that you have to do the corresponding transformation of the ladder operators, which yields the following result, which is shown here. And there is a little bit of math between this part and that part. You have to use essentially the Taylor decomposition of the of your operator U, and you have to use the commutation relations. There is a little bit of mathematical calculations here and there, but nothing complicated. And then if you use basically this result, you can substitute it into our initial expectation value formula and obtain a very simple result, which just yields us that this expectation value is essentially the oscillating field with the amplitude absolute value of alpha and phase phi equal to the argument of alpha, where alpha is once again our complex amplitude, our displacement amplitude, which is a complex number. So what this result essentially tells us that these coherent states are the most classical quantum states because their expectation values obey the classical equations of motions, such as we can obtain from the Maxwell equations. Going next and talking about different Gaussian quantum states, we can bring up another important example in the form of thermal states, with the corresponding number of thermal photons n. Thermal states are relatively simple because they can be viewed as broadened vacuum states. So this is basically our vacuum state here, which is shown by the blue 1/e contour of the corresponding Wigner function. And then the thermal state, which would have one thermal photon, which just looks like a slightly broader Gaussian state. This is the corresponding Wigner function, which is described by this also relatively straightforward formula. For us, what is important to remember that in the high temperature limit, when KBT is much larger than h omega k, the thermal states can be also considered to be classical in the sense that they also do not allow to generate entanglement. However, in modern quantum optics, there is lots of discussions what happens when KBT is on the order of h omega k, because then some people still manage to find some, let's say, non-classical properties of thermal states, which lead to finite quantum coherence or quantum discord, which sometimes can be also used for certain, let's say, semi-classical tasks. So this topic is not fully closed at the moment, how kind of quantum these states can become in the opposite limit when temperatures are relatively low. But I won't go deep in the detail here about this topic. The corresponding covariance matrix and displacement vector for these states look as it is shown here. So displacement vector is obviously 0, and the corresponding variances, the diagonal entries of the covariance matrix, simply look like enlarged vacuum variances. The most interesting and the third type of the Gaussian quantum states, which we are going to need today, is the so-called squeezed vacuum states, which are typically determined by the complex squeezing parameter psi, which is a product of the squeeze factor R times e to the power of if of I, which is the squeezing angle. Those states already are pretty much very quantum, in the sense as we are going to see they can generate entanglement. And they are already very quantum in the sense that if you look at the 1/e contour, after applying this squeeze operator to the vacuum state, we are going to see that you can actually reduce the variance of your fluctuations below the fundamental vacuum limit. For a very long time, people thought that this is impossible, but then, roughly, I think for the first time 50 or 60 years ago in quantum optics, it has been demonstrated by using optical parametric amplifiers that actually you can reduce vacuum fluctuations below the fundamental limit, and this, of course, was kind of a great achievement. But of course, then you have to pay the price and you have to anti-squeeze the conjugate quadrature so that the total product still holds the Heisenberg uncertainty relation, such that as a result, the corresponding Wigner function will look like such kind of squeezed Gaussian profile, which is described by the corresponding simple mathematical formula here. The Wigner function here is, of course, still larger than 0. This is something you have to remember. And as I have already said, squeeze states are non-classical in the sense that they can produce entanglement. And the corresponding covariance matrix and displacement vectors are shown here. So covariance matrix is rather complicated in its general form. However, very often it can be greatly simplified by going in the so-called standard mode or in the standard regime of the covariance matrix, where you essentially diagonalize it, and then you have only two terms, two diagonal terms, and one of these terms would describe the squeezed variance, while the another term would describe the anti-squeezed variance. Let us go next, and at the last slide, when talking about the different Gaussian quantum states, I would like to offer an alternative picture of them, because I can imagine when by looking at these Wigner functions, it might be difficult to understand what kind of fields they are. And for this reason, here on this slide, I show the time dependence of, for example, electromagnetic field E as a function of time, which would correspond to the, for example, vacuum state. So, of course, in order to observe such kind of vacuum state, we would need to have some kind of ideal quantum detector with its internal noise below the vacuum limit, which is physically impossible. But in theory, we can imagine such a construct, and then we would sample our vacuum fluctuations. We would see basically such kind of fluctuations with a certain variance. And this would be the corresponding Wigner function or maybe some other quasi-probability distribution such as the P function. Next, we can consider the coherent states, which would look like the displaced vacuum states, something we already discussed. And the time trace of these coherent states would be simply oscillations with a certain amplitude and phase, and still with vacuum noise on top of them. And this is probably also pretty obvious. What might be less obvious is how the squeezed vacuum states look like as a time trace. Because in this situation, squeezing means that at certain moments of time, our variance of our internal vacuum fluctuations will be suppressed below the fundamental vacuum limit. And as the consequence of the Heisenberg uncertainty relation, we have to anti-squeeze this variance at other moments of times above the vacuum limit, so that the product of these two variances still fulfills the Heisenberg uncertainty relation. And that's the important part of this intuition. Then, respectively, you can also talk about more complicated squeezed states, such as squeezed coherent states with amplitude squeezing or phase squeezing. And you can also introduce more complicated states by, for example, considering squeezed thermal states or squeezed coherent thermal states. So you can start combining these different operations together in various ways. Now, after having introduced the basic Gaussian quantum states, so which in principle can appear both in optics or microwaves in our frequency regimes. So at the moment, we are not really limited to any frequency range. We can go back to our quantum information processing purposes and talk a little bit about the requirements for universal quantum information processing. Very briefly.
Very shortly interrupt you. There is a question in the chat.
Yeah, sure.
In what sense do the squeeze states produce entanglement?
I'm going to explain it roughly in 3 or 4 slides.
Excellent. So, okay, sorry for interruption.
And if something will be unclear, we can talk about it. Is it okay?
Yeah, sure.
Okay, great. Because I'm going to come to that. But first of all, I just wanted to mention that for the purposes of universal quantum information processing, when we are talking about discrete variables, we usually should remember that in order to do universal quantum computation with them, we have to consider a certain universal set of, for example, qubit gates, which typically include, for example, the single qubit Hadamard gate, single qubit rotations, and then the 2-qubit gate CNOT. In principle, one can analyze the continuous variable regime in the same way and introduce another corresponding set of universal gates for the continuous variable regime. Those will be slightly maybe less known to you gates, such as the single mode Gaussian Fourier transform or displacement operation, which we already mentioned because it generates the coherent states, and then single mode non-Gaussian cubic phase gate, which is one of the most complicated continuous variables gates to experimentally implement, and then another 2-mode so-called Gaussian sum gate, which is in principle, I'm going to mention, it's in principle also not so easy to implement, but also possible. Now, when talking about displacement operation, I just want to mention very quickly that the displacement operation, because now we realize that it is not just related to the coherent states, but is also a gate for continuous variable information processing. It's in principle corresponds to simply such kind of geometric displacement operation as it is outlined by this picture. And this is the corresponding operator. One in principle can look how we can implement such a gate. And in optics, this operation is implemented by using very asymmetric transmittive beam splitters with, for example, 99 transmissivity in one direction. And in microwaves, as we in principle studied with in this paper, one can achieve the same result and implement the same logical gate by essentially using, for example, directional couplers, which you can commercially buy nowadays, and which geometrically look simply like such kind of 2 superconducting lines or normal conducting lines, but preferably with low losses, which have a very weak coupling between, for example, this input port, which is called the coupled port. And this is, we insert some kind of quantum state psi here, for example, and here we insert a very strong displacement tone, and at the end we obtain something like psi plus alpha, this is kind of the result of this displacement operation. And one can test that it indeed works like that. And a little bit of mathematical theory behind this process can be found in these equations or in this famous paper by Paris. Yeah, and now I would like to talk about the second gate, which is the Fourier transform gate. And here I'm also going to try to explain you the first kind of point where quantum information processing with continuous variables might be advantageous as compared to the discrete variables. As we already learned yesterday from the lecture of Yuri Machlin, the Fourier transform with discrete variable requires roughly n² quantum gates and is implemented by this rather well-known algorithm. And this quantum Fourier transform is, of course, very important because it's a part of many other useful algorithms, such as the Shor algorithm or phase estimation algorithm, among others. But in principle, one can think how we can make this protocol faster. And here we can remember that, for example, in classical information processing, this way is known for already at least many decades. I learned it myself when I was a student myself 20 years ago, but one can encode in principle your discrete states in the continuous basis as a kind of pulse of light, and then you send it to a lens which generates certain diffraction pattern, which essentially performs this Fourier transform for you. And this is how classical analog computers might work, and they have been built. But in this regime, it was always very difficult for people to combine optics with semiconductor computers. And this is, I think, what is actually can be done easier with superconducting circuits, because here we don't really have to use optics. We can use the optics on chip by using superconducting materials. Because then, essentially, the Fourier gate or Fourier Gaussian gate in continuous variables can be achieved by an application of a simple resonator Hamiltonian for a quarter of a period, which means that we can encode some information in a propagating photonic mode, and then, for example, inject it into a tunable lambda half resonator, and then we can make a zero-step or one-step operation. For example, zero-step operation just means we encode our operation in P quadrature, we insert it in the resonator, and then we couple to the Q quadrature somehow. And then we immediately instruct the Fourier transform. Or we make a one-step operation when we encode something in P, then we wait for a quarter of the period of oscillations, and then we extract the Fourier transformed amplitudes from the same Q quadrature. So there are different approaches, and you can find the description of these different approaches in these papers. Of course, I was in principle, this is a rather well-known thing, how that in principle it can be possible, but when I was talking about it, I, for example, remember Alexey Ustin was also asking me this question a couple of times in the past, but how we can encode qubits in continuous variables. And here now, finally, I came with at least a particular protocol, how to do it, and this is what I'm going to quickly explain it to you and give you some idea. This protocol is not extremely simple, but it's described in this paper. It essentially consists of using two coupled resonators, A and B, which are coupled via cross-Kerr interaction. And then you also start with n qubits in the beginning, which are far detuned from both resonator modes A and B. Then, in order to perform the Fourier transform of these n qubits, you tune qubits sequentially one by one in resonance with the resonator A. Then you start, of course, with uncoupled qubit eigenstates, which encode your logical information. And then you swap the qubit states into resonator A by applying a certain frequency control fields, which essentially do the swapping operation as it is shown here for the example of these 3 qubits. And essentially you encode your qubit states in dress states in resonator. So such kind of dress states which are shown here and which are in principle also very well known from circuit QED, and this is what I think Arkady Fedorov mentioned yesterday. In principle then we can do the Fourier transform. We only have to require that the second resonator B must be prepared in a very specific state, which is the superposition state between certain number of Fock states. That's kind of the caveat of this protocol, but we found out that there are certain kind of papers, such as I think this paper from 2018 from Martinez, which allows you to achieve these tasks for this polynomial time scaling, so it can be done by using an extra ancilla qubit. And then essentially all you need to do is you simply have to wait. So we allow for a free evolution of this cross-scalar coupled resonator system, which performs and delivers you the answer in the resonator B in form of the Fourier amplitudes of your initial qubit states, which at the moment is also entangled with the A resonator, which means that you have to apply certain disentangled projection measurement of the resonator A, which can be also performed in a certain way, which I don't go here deeply in technical details, so I ask you at the moment to believe me that this is possible, but if there are some questions, we can also discuss them a bit later. And then as the result of this protocol, one in principle can show how the scaling of this continuous variable QFT protocol works for a particular Q-dimensional phase estimation problem, which uses the QFT, and then you can show that this continuous variable approach scales linearly with the number, with the dimension of the Hilbert space Q, or with the number of qubits, as opposed to this square scaling for the conventional approach. And this is obviously the advantage of the continuous variable process. So now I go exactly to the question which has been asked a little bit earlier about the quantumness of squeeze states and how we can actually generate entanglement here. In principle, this is a very well-known thing which is known from quantum optics. Once again, the notation of entanglement between certain subsystems is related to the notion of the product states. This notion goes as follows: we have a kind of composite quantum mechanical system, and we can write its full wave function as a product state with the corresponding subsystem wave functions psi1 and psi2, then by definition those subsystems are not entangled. But if for some reason this description is not possible, then we call this composite system to be entangled. And the most known example nowadays of the entangled system is, for example, represented by two entangled qubits, which are in the corresponding Bell state, which is here called psi plus. But there are a little bit different notations for the Bell states. In continuous variable regime, those entangled states they look a little bit different. They are known historically as the EPR states, and they can be represented by these delta function correlations, for example, of different quadratures of the electromagnetic fields, such as the correlations between the quadratures Q1 and Q2. And with such kind of states are known as the two-mode squeeze states, because this squeezing now occurs not in one local mode, as it was the case for single-mode squeeze states, which we have introduced a few slides above. But now those correlations are distributed between non-local quadratures, which essentially captures the essence of entanglement. But entanglement at the end of the day, this is nothing else. At least this is how I understand it. These are just correlations which might be stronger than any possible quantum classical correlations, because you essentially those correlations can go beyond the fundamental vacuum limit. And we'll now finally, or hopefully the answer to the question is that the squeeze states are non-classical in the sense that by sending a simple squeezed vacuum state to a symmetric beam splitter, you can automatically generate so-called path entangled states at the output of this beam splitter. Technically, we have to remember that here there should be another input, which is because beam splitter is always a kind of 4-port device, but here we can consider that we insert the vacuum state. And still in this situation, you will generate entangled states. And this is not possible to achieve with any other states which we normally call classical, such as thermal states or coherent states. In the microwave regime, we don't have really beam splitters. But we have the devices which are known as the hybrid rings, which are very similar devices. These are also 4-port devices. So this is how they look like. This is essentially simply an interference type of device, where basically this distance corresponds to, I think, lambda half of the corresponding wavelength. So hybrid rings always have a limited bandwidth in which they operate. And then these differences, I think, they correspond to lambda 4. Of the corresponding wavelength for the corresponding frequencies. And yeah, this is another input, which in this case is just vacuum state. So this is how we generate our entanglement, and this is why I call squeezed vacuum states to be quantum, because it's not possible with any other states. There is also a different aspect to squeezed vacuum states, why I also can call them quantum even without talking about entanglement. In principle, you can see that if you take a displaced squeezed state, you can, in principle, in a certain range of displacement and squeezing amplitudes, you can achieve the so-called perfect anti-bunching of photons. So you can, with displaced squeezed states, in principle, you can achieve something which I will very loosely call the single photon source, even though it would be a very big single photon source in the sense that it would have a very low brightness, but still fundamentally possible. And this is possible in the situation when displacement amplitudes and squeezing amplitudes are aligned along a very specific axis in the phase space. So there are many general applications of this entanglement, such as, for example, the applications in quantum communication, quantum information processing, or sensing, and many of them you definitely have heard about or know. And today I want to mention some more novel applications, such as remote qubit entanglement applications, or a rather novel field of Gaussian boson sampling, where entanglement can be used for information processing purposes. So let us first start by talking about the remote qubit entanglement, once again to establish a better link between continuous and discrete variables and show how these kind of different approaches can be used in the hybrid regime and where we can benefit from both of them. Let us imagine that we have a task, that we have two remote qubits which we would like to entangle. This is our task. The first question is how we can achieve it. At this moment, you can also ask me already, why do we want to achieve it? And here I just prepared a short motivation slide that, for example, if you start looking, for example, at various roadmaps for various companies, such as the roadmap from 2020 from IBM, which is still online, I just checked it half an hour ago, you can find out that even those people who prepare some huge fridges, which are planned to hold thousands or at least hundreds of qubits, already they admit that there will be no way to house maybe millions of qubits in these big fridges because of various connectivity issues. And eventually they envision a future where they must use quantum interconnect links between separate dilution refrigerators in order to build superconducting quantum supercomputers. This is why we need to develop certain protocols how we can entangle these remote qubits. And one particular way of entangling them is to use this path-entangled continuous variable radiation in the form of two-mode squeezed light, and simply shine this light at resonance on our superconducting qubits. So this is the so-called resonant regime, and if you look at the literature, you can find out that this protocol has been considered as applied to the cold atoms already some almost 20 years ago by Zarak and Krauss in 2004. And then they observed a very interesting result that in principle you can quantify how much entanglement in the qubit you can generate by using the so-called entanglement of formation criterion, which is limited by 1 in the case of ideal entanglement between these two qubits. Yeah? So 1 is the limit of, it corresponds to the perfect entangled qubits. And then what is interesting, you can compare this to the amount of entanglement in the squeezed radiation. And this amount of entanglement of formation in the two-mode squeezed radiation is not bounded. It can go to plus infinity, which corresponds to infinite squeezing. But in this case, you observe a very interesting result that the amount of entanglement formation between qubits kind of goes towards 1 only in the limit of infinite entanglement. So it means that you can ideally entangle two qubits while being in the resonant regime only when you produce infinitely squeezed states, which is obviously problematic. And as a result, this protocol also is very susceptible to external noise and transmission losses, because the external noise and losses which affect your two-mode squeeze light, they will inevitably reduce your squeezing level, and this is why you will also reduce the amount of qubit entanglement of formation. So one can in principle try to do better than that, and in particular I like this paper by the group of theoreticians from France and Yale from Mirahimi's group, which was published in 2018, they proposed to use a more interesting dispersive regime of entangling, remote entangling of qubits by placing these qubits into two cavities, where qubits are dispersively coupled to these cavities, and drive not the qubits directly, but rather driving their resonators with the two modes squeezed light and by applying driving tones to the qubits, as it is shown here, essentially by creating weak-Rabi oscillations in the qubits. Then one can show that there is an extremely interesting, essentially dissipative dynamics happening there, where you use both the two modes squeezed light and internal weak dissipation in order to steer these quantum bits in the entangled basis. And the interesting thing about their protocol, which they characterize, for example, here in terms of fidelity of the Bell states. So fidelity equal to 1 corresponds to an ideally entangled qubits. And here you can see that even if you start with very limited two-mode squeezing, such as 6 dB, which is by far below the infinity, you can still reach ideal entanglement just by waiting a certain amount of time, which can be estimated with here it's measured in terms of inverse kappa, which is the relaxation rate of these resonators. But one can also put all reasonable numbers and obtain that this kappa would be on the order of 10 microseconds, and which would be also the limit for the coherence times of the qubits, which are very well accessible coherence ranges for state-of-the-art superconducting qubits. So this is essentially a beta variant of this protocol, which maybe somebody will implement and experimentally test one day, which I find to be very interesting because it also if you look, this paper is very theoretical, I have to admit. They don't explain everything very much in terms of physical intuition, but they claim that dissipation plays this decisive role in essentially steering this quantum system in the entangled state. So as far as I understood, without dissipation, this protocol wouldn't work. And hopefully one day we can investigate how in fact does it work. Here, I would like to present the third and the last protocol for the quantum information processing, which characterizes the power of continuous variables, which is provided here by the so-called Gaussian boson sampling, which is in theory is a very interesting protocol which involves using multiple single-mode squeeze states, which can be injected in a rather big linear network, which encodes a certain essentially connectivity graph G, and which as the result, we already have seen that if you inject one squeeze state and one beam splitter, you generate a two-mode entangled state. And you can imagine if you have a complicated n square mode network and you inject n single mode squeeze states and also n mode vacuum states, you will generate n square entangled or multi-mode entangled states, which corresponds to a very big Hilbert space, which in principle grows at least exponentially with the number of modes. And additionally, it can also become even bigger if you consider the finite number of photons in those single mode states. And then the interesting thing which people realized that actually by sampling the outputs of this network by using single photon detectors, one can get an access to this Hilbert space, which grows exponentially. And this way, one can gain an access to certain mathematical functions, which are extremely difficult to compute by classical computers, such as the permanent, which is just a function of this graph adjacency matrix, or Hafnian. These are some kind of mathematical functions, where I'm not really an expert, I know only some basics, but these are the so-called sharp P complete complexity classes, which cannot be efficiently solved even on classical supercomputers. And such kind of functions can be actually sampled relatively easily experimentally by measuring the corresponding covariance matrix of this entangled state, and essentially which can be achieved by sampling the number of photons, which can be done routinely by using single photon detectors. And what is, of course, also important that people managed to find that certain applications can be mapped on these graphs, adjacency matrices, such as certain graph-based problems, or more specifically quantum chemistry problems associated with simulation of various vibrational modes of complex molecular And this is, if you're interested, you can look up in this Nature Photonics paper, which explains this mapping details a little bit. So essentially, this is what we can already kind of envision doing. But recently in 2020 and 2029, there have been two papers. One of them is already published in Science, and another one is still in the stage of a preprint, which demonstrated the power of the squeezed light by preparing many squeezed single mode states and sending them to such kind of a massive network of beam splitters, where they managed to basically sample certain click numbers by using essentially a big number of single photon detectors, and then they simply estimated how long would it take to simulate those quantum outcomes or measurement outcomes by using their best available to them supercomputers. And these are some crazy numbers on the order of 10 to the 14, which simply tells us that simulating of such kind of quantum experiment would be absolutely impossible by using classical supercomputers. In a way, this experiment simply demonstrates us another quantum supremacy or quantum advantage experiments, which are very similar to maybe a little bit more well-known John Martini's experiment, which has been implemented a little bit earlier with superconducting bits. But here we use just squeeze states and linear networks. And even though, once again, those all experiments, some people can say they're not super useful at the moment, but they demonstrate a lot of potential, and maybe we can do something useful with them. So here I'm finished with my introductory part, which honestly took a little bit longer. Maybe there are some questions. I cannot see chat, actually.
Well, there is nothing in the chat at the moment.
Okay, good. Then I will continue with the second part of my lecture, which will focus more about how we can actually generate these squeezed microwaves by using the so-called geostorm parametric amplifier to perform vacuum squeezing, and then how can we measure them or generate microwave two-mode entanglement. Essentially, this is just a little bit of motivation, which probably I would like to skip because I'm a little bit running short on time. Like, why do we consider microwaves? Well, just because they are so great for communication, sensing, and distributing computing purposes. And one of the particular reasons why they are so great is just that we can look at atmospheric transparency windows where we can compare the microwave losses at the frequencies below 20 GHz to the optical losses, for example, at the infrared range or optical range. And then you can see that essentially optical losses are by 1 or 2 orders of magnitude worse. And additionally, those optical transmittivities, they are very strongly affected by imperfections, atmospheric imperfections, such as fog, rain, and haze, which is in contrast, once again, to microwaves, which are less affected by these imperfections. And additionally, our superconducting quantum circuits, such as superconducting bits, they naturally operate in the gigahertz range, which means that if you want to communicate between them, microwave regime is the natural one, which is, of course, has its own problems and certain challenges. One can also ask a question how well we can communicate not through the free space, but via superconducting environments, such as superconducting cables. And then one can, for example, look at the state-of-the-art measurements, which have been performed, for example, by us or other groups, such as, for example, Andreas Walther group. And then one can see that the losses in the best superconducting cables or waveguides are very much comparable to the losses in typical commercially available fibers. At this point, usually sometimes some quantum opticians, if I talk to them, they explode and tell me that actually these losses, these are just some average optical fibers, but in fact, they can be at least 1 order of magnitude better if you buy some super expensive low loss optical fibers. Well, in this kind of case, you can also notice that if you, for example, just take some very mediocre aluminum cavities, and with reasonable coherence times on the order of 1 millisecond, one can calculate what is this kind of total length which photon passes when it bounces back and forth in this cavity during this coherence, which kind of translates into distances on the order of 10 to 100 kilometers, which translates into the losses on the order of 10 to minus 4, 10 to minus 5 dB per meter for the corresponding to be built aluminum waveguides. It simply means that we are not, if we kind of make all those connectors in a very lossless way, we can remove or we can greatly reduce our losses per kilometer also with superconducting cables. So we are not yet limited by the material properties, and there is a lot of room to go. So, and essentially, my main research topic of interest is how we can use those propagating microwaves in the form of squeezed light for performing quantum communications towards building quantum internet or distributed quantum computing or quantum key distribution or quantum radar. These are all the topics which are very dear to me, but today I'm mainly going to focus on some questions regarding quantum communication. But before going into this topic and quickly telling you about some related physics, I would like to be a little bit more pedagogic and tell you how we can actually squeeze microwave states and how we can understand the underlying physics. In principle, squeezing is nothing else, it's just a phase-sensitive amplification with low-loss environment. So we can borrow the concept from classical radio physics. In order to achieve any kind of amplification, we always need a nonlinear medium. And in this case, we can create a slightly nonlinear superconducting medium, which can be easily achieved by using a nonlinear resonator, such as a CPW resonator with a DC squid, which nowadays is very well known by the nickname of the Josephson parametric amplifier or the GPA. This is how such kind of devices usually, this is at least one of the certain versions of these amplifiers, which is the flux-driven GPA, which consists of tunable lambda quarter wavelength resonator, which operates at a fundamental frequency omega 0, which is additionally short-circuited to the ground with a DC squid, which is just a superconducting ring with two Josephson junctions, which are shown here with the crosses. And this resonator can be tuned by controlling the magnetic field or DC magnetic flux through this DC squid. And then essentially to make this device to work as a squeezer, we additionally have to provide a microwave strong pump tone, which must be applied through the pump light, which inductively weakly couples to this DC squid loop and induces a radio frequency flux, which creates the so-called parametric pump. Such kind of system in its most simple situation can be described by this very straightforward Hamiltonian, which consists of two parts. The H0 part, the kind of unperturbed part, is just our harmonic resonator, which is slightly has a small nonlinearity, which is caused by the parametric pump, which affects our DC squid at a frequency 2 times the frequency of the oscillator. And this is simply the kind of first order nonlinearity, which is described essentially by the square of the quadrature, or which can be expressed as the sum of A plus A dagger squared. So the exercise which we can do here, which I find always to be very instructive for myself and for my students when I read about this during my lectures on applied superconductivity, is that one can actually demonstrate that this Hamiltonian indeed implements the squeezing operation. In order to demonstrate that, we once again can go in a certain interaction picture as described by this operator U with the corresponding energy H0. So essentially in this frame, we simply subtract the energy of the unperturbed oscillator. And additionally, we have to perform the rotating wave approximation and introduce a new parameter lambda, which is simply equal to omega 0 times epsilon, simply to simplify our math. As the result of this operation, which I leave to you as a small homework, one can arrive to this type of interaction Hamiltonian, which is shown here. It's rather straightforward. And then we can use the rule, which has been yesterday also discussed by Yuri Machlin, and assume a unitary evolution such that the corresponding evolution operator is written as the exponent of this time-independent Hamiltonian. And then we can look up how we introduced our squeeze operator, and then we can immediately realize that this unitary operation for the intra-cavity field exactly coincides with the squeezing operator, provided that we unified the product of time times our parameter lambda as a new parameter, which we define as the squeeze parameter. And another alternative way to show that indeed this Hamiltonian implements the squeezing operation is to consider the quadrature evolution of the intrafield inside of the resonator. For that, typically one can write the corresponding Heisenberg equation of motion for the time-dependent operators A, which is by definition equal to this commutator of A and interaction Hamiltonian. And one can calculate that this will be nothing else but lambda times A dagger. So that the solution of this differential equation for the operators will be essentially provided by this Bogoliubov type of solution, and which can be rewritten in terms of quadratures by using the canonical relationship between the ladder operators and quadrature operators in the following form. So then the final step is simply to estimate the expectation values for the variances of P and Q, and then automatically one arrives at the result that one quadrature will be infinitely anti-squeezed in time, while another will be squeezed in time. So that eventually doesn't matter what were your initial conditions, it can be at vacuum, it can be at thermal state, but eventually due to this exponential scaling, we will always squeeze one of the quadratures below the fundamental limit, quantum limit. And you will still, as the result of this evolution, you will still preserve a Heisenberg uncertainty relation. So that kind of, we are not really breaking quantum mechanical laws here. And this is the way how to see that this Hamiltonian indeed implements the squeezing operation, and such kind of tunable resonator indeed can work as a microwave squeezer. In experiments, these devices essentially, this is how the measurement response of such device looks like. So it's a tunable resonator which frequency we can tune with a constant flux, and this is the characteristic response, which can be fitted pretty nicely by using the flux-dependent formula for the DC squid inductance. And actually the physics of this squeezing, if you don't kind of, even if you have troubles understanding the quantum mechanics and these quantum mechanical formulas, one can really easily understand it by considering the parametric excitations of a child who is parametrically exciting a classical swing by modulating its length or its moment of inertia with the frequency 2 times the frequency of the pendulum itself. So it's actually pretty much a very well-known classical parametric resonance, which is translated to the quantum realm. And then this is basically what we can measure experimentally. We can send the vacuum state, which means that we simply cool down, for example, a 30 dB attenuator to the temperatures something in the order of 10 millikelvin, so that the thermal contribution is very low. We attach it to the input of our GPA. Of course, we have to use an additional circulator here in order to separate between incoming and outcoming waves. And then in reflection, if we pump this kind of GPA, we can experimentally measure such a nice Wigner function of a strongly squeezed vacuum state, which is here is squeezed by 6 dB below the fundamental vacuum limit. And this state is already propagating through our wires, and it can be used, for example, to generate entanglement or perform some computational tasks. This is how these devices typically look like, at least in our lab. This is the small GPA chip, and this is how it looks like when it's closed. And this is a rather big magnetic coil, which provides with the DC magnetic field, which we need in order to tune the working point of this device. And this small simulation also shows you how the input state is being transformed into the output state for the increasing pump outs. And you can see how the squeezing level increases and how the number of photons increase as a function of the squeezing. This squeezing level is typically measured as a function of, it's essentially a logarithmic scale, which simply is kind of takes the ratio between the squeezed quadrature as related to the vacuum variance. Right. The last question here is actually how we can reconstruct those Wigner functions, because this is something which might be not at all obvious. So far, I completely omitted this question. Because we don't have commercial microwave single photon detectors, not yet. And our off-the-shelf linear amplifiers, as already have been mentioned on a couple of occasions, they are very noisy. They add a lot of noise. It means that we cannot just do some homodyne type of detection in the quantum optics manner and reconstruct our density matrix in the fog basis or something like that. So we have to use different approaches. And nowadays, there are two main approaches. The first of them is to use parametric superconducting preamplifiers and qubits in order to sample our essentially density matrices or amplify our signal in a very noiseless way, which is sometimes problematic because that means you have to use more superconducting hardware, which you have to control and which sometimes creates problems. So we usually apply a different way here by using the so-called signal recovery methods, which essentially exploits measuring statistical moments of our signals. Let me quickly explain how does it work and what is the advantages of this approach. For example, let us imagine that we have a very small signal, which is described by the operator A, which consists of very few photons. And then what we actually can do, we can split it into two paths, and of course then add the corresponding vacuum operators to these inputs. And then we can independently amplify them with two very noisy amplifiers. So that the resulting kind of states are very noisy states where our signal is completely covered by this very strong noise, which is several orders of magnitude larger than the signal. Then, in principle, we can notice that knowledge of all the statistical moments of our signal, AN, is equivalent to the knowledge of the Wigner function or the density matrix. In principle, we can simply try to average for a very long time in order to extract all the statistical moments, AN, and reconstruct the Wigner function and, for example, the density matrix or the covariance matrix. However, there is here a problem that if we start averaging the signal, sometimes it works. For example, for first order moments, we can indeed average and then we simply cancel out this noise because we usually expect that the mean value of this noise is 0, which is usually the case. So it's possible to measure the average value, the expectation value of our signal. However, in order to, for example, reconstruct the covariance matrix, which already requires measuring the variances, this is not possible because if you evaluate how the noise enters in the second moments, then you will immediately obtain the result that it's kind of enters via the corresponding variance, which is not equal to 0. This is why already reconstruction fails for the second order. However, in this dual path approach, one can do a trick and one can actually measure not the self moments, but the cross moments, which means that you don't measure C1 squared averaged, but C1 times C2. So you measure the correlations between these two inputs, which are referred to the same input at the cryogenic stage. And by doing so, you can, and using the fact that these noise contributions high 1, high 2 uncorrelated, which means that this product will go to 0, one can nicely obtain, for example, the variance of our signal. And then one can use iteratively this approach in order to reconstruct all the moments up to at least the second order in order to perform the covariance matrix reconstruction. And by doing so, as we have already discussed, one can reconstruct the Wigner function of propagating microwave quantum states. And this I can illustrate by, for example, looking at some typical experiments where we use two GPA, two squeezers in combination with the beam splitter in order to check the experiment on generating of these two mode squeezed states, which are propagating along path 1 and path 2. Here, basically, I show the experimental tomography results as a function of the squeezed inputs from GPA1 and GPA2, which you can see on the left-hand side, which are entangled by using the microwave beam splitter, the hybrid ring. And then we have some local outputs and non-local outputs, which are quantified by the cross correlations. In the case when GPAs are squeezing the field in the parallel direction, we can actually obtain an important result that we don't see any cross correlations. We have symmetric distributions. And also if we try to measure negativity, which kind of quantifies the amount of entanglement, we see that this negativity, or specifically talking negativity kernel, is less than 0, which means absence of any entanglement. However, if we rotate our states, we actually, and when the squeeze states are orthogonal to each other, you can produce a very curious result that locally your states will look like thermal states, essentially like noise, which nevertheless exhibit very strong correlations between the non-local quadratures, such as the quadratures of P1 and Q2. which essentially captures the essence of entanglement. Yeah, and this is simply the experimental demonstration of possibility of creating entangled microwave states. So now I'm in principle hopefully convinced you that we can generate these squeeze states, we can measure them, and we can also generate two-mode entanglement. In the last 10-15 minutes of my lecture time, I would like to very quickly go through certain protocols, how we can use such kind of propagating entangled microwave states for the purposes of quantum communication. And here, in principle, I will very quickly go through two protocols, such as remote state preparation protocol or quantum teleportation protocol. Let us start with the first one. I suspect that this protocol might be not very well known because it's kind of not maybe as known as the quantum teleportation protocol, even though it's also very useful. And to introduce this classical, remote state preparation, we consider the scenario when we have two parties, Alice and Bob, and Alice wants to prepare a certain quantum states at a distant location by using a local operation. Essentially, in order to perform this task in the classical sense, Alice simply has to send all information about her state she would like to prepare at Bob's side. If we are talking about pure squeeze states, those states are quantified by two real numbers, which means that these two real numbers must be sent with a certain precision from Alice to Bob. And this is the price of preparing this state. However, it turns out, as it was found in this paper 2001 by Bennett, that one actually can implement this task more efficiently by using entanglement, pre-shared entanglement. One can reduce the information price by a factor of 2 by pre-sharing entanglement between Alice and Bob. And this is what we actually managed to implement in the microwave domain over a distance of roughly 30, a little bit more than 30 centimeters, by using our already studied entanglement source, by using two GPAs, and by adding the third GPA, which is used here in the regime of very strong and noisy phase-sensitive amplification, which essentially can be used as the way for Alice to generate this classical signal, which is very noisy, which doesn't have any quantum properties, but which encodes the classical information in its phase and amplitude, which is sent to Bob, where Bob implements this displacement operation in order to prepare the squeeze state. And this is, of course, very curious because we should remember that just if you would have no entanglement, just by using any kind of displacement operation, we can never prepare any kind of squeezing, right? I hope that's obvious. But in this protocol, this is one of the results at the optimal working point that, in fact, if you use entanglement, you can prepare a distant squeeze state just by using entanglement and displacement operator. This squeezing level is not too much, but it's still 1.6 dB below the fundamental vacuum limit, but still very finite. And this is something, then you can study how different parameter regimes affect those states. And this is something I think is not very important for us. And I rather would like to spend my remaining minutes on telling you how about an interesting twist of this protocol, which can be treated as the so-called quantum version of famous one-time part. Probably some of you know about this cryptography protocol, which is one-time part, which has a goal to send a message M from Alice to Bob. Apparently, even in the classical regime, one can achieve this task unconditionally secure if one generates a uniform random key and distributes it between Alice and Bob in the way how it is shown here. And then Alice can use a certain procedure in order to generate the secret, so-called cipher, which can be then sent through the public channel, which can be eavesdropped by the competitor party, which is usually known as if, which in principle tries to crack our protocol. And then one can show that as long as this key is as long as the message or longer and is absolutely random, this protocol is completely unconditionally secure. This has been demonstrated by Shannon mathematically by demonstrating that in this particular scenario, the Shannon entropy of the message is equal to the Shannon entropy of the message given the cipher, which is the mathematical way of expressing the fact that knowledge of the cipher doesn't provide us with any information about the message. So this is in big kind of contrast with known RCA asymmetric protocols, cryptography protocols, which in principle can be cracked. But this protocol, as long as the key is long enough and completely random, it cannot be in principle cracked, because all possible outcomes of the message which you can extract through the cipher, they all have the same probability. And this is the mathematical proof of it. So let me quickly illustrate it. Let us take the message, which is winter is coming. This is just the wording, which we are here use an obsolete writing for the word coming with 2 N's. In principle, you can assume that I made a typo. This is very useful for us because then I can encode those letters by using their position in the English alphabet. And for these 2 neighboring N's, of course, they are encoded by the same number. And then I just randomly generate some key, which is just the sequence of random numbers. And then I add these numbers together and take the mod operation of the result, which generates me the cipher C, which here immediately shows to me that those neighboring letters M are encoded by completely distant and uncorrelated numbers, which essentially captures the essence of the unconditional security of this protocol. This one-time pattern principle is a very cool protocol, but it has kind of several big limitations. First of all, the key must be long enough and must be securely transmitted between Alice and Bob. And second, this key must be absolutely random. And this is actually what is very difficult to achieve in the classical realm, because all those pseudo-random key generators, they are not completely random. But in our RSP, we have access to entanglement. And one can actually notice a very interesting reinterpretation of our RSP protocol on the language of the cryptography protocol, where we can actually treat our message M as the RSP state, which we are trying to remotely prepare, or which we essentially are trying to send from Alice to Bob. And the key K is essentially provided by the correlated vacuum fluctuations, which are ideally and ideal random fluctuations which don't have any deficiencies of pseudo-random generators. And then with cipher C, this is essentially our quasi-classical feed-forward signal, which we prepare at Alice and send to Bob. Which means also that we can try to experimentally check whether this assumption is true and whether our protocol is indeed secure by looking at the corresponding difference between 2 entropies, which in this case should be not Shannon entropies, but the so-called von Neumann entropies, which we can obtain by performing full state tomography with our covariance matrices. And from these covariance matrices, one can faithfully calculate the von Neumann entropy. And then one obtains a cool result that at the optimal point of our protocol, this difference between 2 entropies is indeed almost 0. Not completely 0 to my kind of disappointment, but due to the fact that this difference is still much less than the self-entropy of the message, usually it means that by applying a certain reconciliation protocol, one can make this communication protocol to be unconditionally and ideally secure, which was for me was always a cool interpretation of these results. Now, provided there are no questions about this part or other parts, not so fine. I then can spend just the last minutes to talk about some of our more recent experiments, which also go in the direction of quantum communication with continuous variables, namely the quantum microwave teleportation, which is better known, which is in principle very similar to remote state preparation, where we essentially teleport in a known quantum state also between 2 parties, Alice and Bob. And in this case, this protocol can be characterized by the corresponding density matrix of unknown input state, which is teleported between 2 parties by using the pre-shared entanglement, which must be pre-distributed. The quantum teleportation protocol is typically characterized by using the fidelity criterion, which simply shows us the overlap between the input and output states in the phase space. And this is its implementation with Joseon parametric amplifiers, where essentially we can recognize that this first part is simply for generation of 2-mode squeezing, which is then distributed between 2 parties, Alice and Bob. And at the end, this is how the setup looked like, which was hidden at the bottom of the dilution refrigerator. So we used essentially 4 GPAs, each hidden in this kind of shielded aluminum box where the fifth GPA, this one in the center, hasn't been used for this particular experiment. It has been meant for something else. And then I can just very briefly go through some part of this setup, such as showing you the characterization measurements of entanglement, which has been implemented first. And then the interesting part of this protocol was the implementation of the feed-forward signal generation, which we have found to be very curious because one can actually obtain an interesting result by looking at the covariance matrices of which combine two hybrid rings, one GPA plus the directional coupler, that the combined action of these four elements in the continuous variable regime can be shown to coincide with the projection operation, where if we tune correctly the amplification phase sensitive axis of this GPA, we can project our quantum state along the certain phase space, along a certain direction in the phase space, for example, along the p direction. And then we can use the second GPA in order to respectively project it along the q direction. And as a result, we can use these two the combination of two hybrid rings and two GPAs in order to perform Bell-like type of measurements, but in continuous variable regime, which I find to be pretty instructive and which is also a prerequisite in order to teleport the coherent state from the input of Alice to the output of Bob, where once again at the end we use just a displacement operator, which has one entangled state as one input and uses the classical feed-forward, which is coming from Alice as another input. And as a result, we can reconstruct this coherent state. And here I can briefly show the tomography of the corresponding teleportation experiment, which most importantly show these tomography results show how the input state looked like and how the teleported state looks like. They are not obviously the same. However, if one calculates the fidelity between these two states, one finds out that first of all, this fidelity is larger than 50%. And at the same time, one can switch off the entanglement in this protocol and obtain an interesting result that fidelity then drops below the 50%, which can be very well understood by analyzing the theory, because theory predicts that this threshold of 50% is the so-called crossover between the classical and quantum realms. In principle, one shouldn't be able to teleport an arbitrary coherent state with the fidelity more than 50% without the use of entanglement. So this is already kind of the experimentally important result that teleportation indeed works in the quantum realm. However, as you can already see from this graph, which plots the fidelity of teleportation as the number of displacement photons for different measurement strengths, which are characterized by the gain of the measurement GPAs, one can actually make this fidelity even greater than the so-called no-cloning threshold, which is equal to 2/3, which essentially guarantees that in this regime, when you teleport your state with even bigger fidelity, which is larger than approximately 0.67%, it means that the quantum teleportation protocols also becomes unconditionally secure because it's essentially guaranteed to you by the quantum no-cloning theorem, which essentially tells you that quantum states cannot be copied. And then one can, of course, analyze these results in much more detail, which I don't have time to discuss. The only thing I would like to end at the end is that we can fit our experimental results with the theory pretty nicely here. For example, those bars, these are the experimental results, and this kind of orange surface, this is our theory, which is also reflected by this full theory graph on the right-hand side, which is a function of two-mode squeezing and measurement gain. And since it fits pretty nicely, we can extract a very interesting result from this fit, that in principle, well, first of all, our teleportation works with great fidelities. Our fidelity limitations, we also understand they are mainly due to losses and GPA noise. But most importantly, we realized from our theoretical fit that we could add much more losses in our entanglement distribution channels and make them, for example, almost 1 kilometer length, because we can tolerate up to 1 dB of losses in the entanglement distribution channels. And assuming that you use superconducting cables with the characteristic loss of 10 to minus 3 dB per meter, then it means that we can add 1 kilometer and perform microwave teleportation over the distance of 1 kilometer. Which kind of brings me to the end of my talk and to the brief outlook, where I, in principle, demonstrated to you some potential for microwave quantum communication and continuous variable processing. And for example, some of the topics which hopefully I will be able to talk in the future is how we are building our quantum local area network in the microwave regime, where essentially we are interfacing two dilution refrigerators to prepare for the future distributed quantum computing. So this is the current system we are testing right now, which is kind of roughly 6 meters long, where we are going to cool down a superconducting cable to the temperatures of several millikelvin. At last, I also have to mention that the topics which I tried to cover in continuous variable quantum information processing, these are not kind of the only ones. There are many other topics such as quantum sensing, quantum radar, or quantum cryptography, or a specific topic which is actively pursued by the Yale group in terms that you can use, one can encode discrete variables and continuous variable basis to implement quantum error corrected computation in the form of the so-called GKP states. But unfortunately, today I didn't have time to talk about all these things. And at last, I, of course, presented experimental results. This is not at all only my kind of result. There is a big group of quantum microwave communication and sensing team, which has contributed to all these results. And I would like to thank them for their contribution. And I would like to thank you for your attention. And I'm ready to take on all possible questions.
Great. Thank you very much, Kirill. Thanks a lot. Well, I personally find this introduction which you gave from textbook very useful for the community here. And obviously, this is the whole big science, but it's not necessarily part of superconducting quantum circuits by default. So I think it was very useful to introduce quantum information presentation in continuous variable. I see one question on the chat. Can you read it? Maybe you could answer directly. I don't have to read it.
Probably I just have to go into the different regime. So
I can read it, no problem. Is there any criteria to differentiate Gaussian from versus non-Gaussian states?
If there is any criterion. So in principle, that's a very old question which we asked ourselves for a very long time. Unfortunately, I'm not aware of any really good mathematical criterion, because the problem is that typically people look at the so-called cumulants, which are a different form of statistical moments which differentiate Gaussian from non-Gaussian states. Unfortunately, these cumulants, they are very often non-normalized, which means that you cannot compare third-order cumulant directly to the second-order cumulant. And so far, we didn't really find any consistent mathematical way how to mathematically kind of introduce a criterion to say that this state is Gaussian and this state is kind of is still Gaussian. And that was always kind of problematic. So usually how we do it experimentally, we just look at all those cumulants up to the fourth order. And when we see that at some point, for example, when we produce squeeze states, if we squeeze them too much, we know that those squeeze states start to look like so-called banana shape if we do the direct state tomography without using any kind of Gaussian approximations. And then you can also see that the corresponding fourth or third order cumulants start to rise exponentially. And then we roughly say, oh, okay, this is already, everything is already bad, so let's reduce our squeezing. But that's it's a very dirty and murky business. So unfortunately, we still didn't really find a good mathematical way. And I would be actually very much interested in finding one, but not yet, unfortunately. So
and then also again from Rajit, for what purposes do we need non-Gaussian states?
Yeah, I now opened
create a gate of continuous variable regime.
So non-Gaussian states, in principle, there are lots of interesting things associated with them. First of all, there is, for example, a theorem, which sometimes makes me a little bit sad, in the sense that with theorems, there is a physical mathematical theorem, which claims that classically you can efficiently simulate any positive dynamics of positive Wigner states. In this sense, one sometimes needs those non-Gaussian states, these negative Wigner functions, in order to reach the regime of this quantum advantage or supremacy. But this is not applied, obviously, to the regime of unconditional security in quantum communication. These are unrelated topics, and one can reach the useful regime of unconditional security by using positive-only Wigner functions. But if you want to reach this quantum supremacy, then typically you need negative Wigner functions, which are always non-Gaussian states. So, yeah. And then the third question is, can we create Schrödinger cat states from GPAs? So technically, yes, but not in the steady state regime. I can send you to the paper by Yasunobu Nakamura, I think from 2018 or 19, where he shows that if you consider the ring up process in the flux-driven GPAs, so when you apply essentially very short pulses, then the output of these GPAs essentially resembles the Schrödinger cat states. And this can be understood also from another perspective, that if you simply look at the Taylor decomposition of the squeeze states, then for very low level of squeezing, Taylor expansion for the squeeze states coincides with the Schrödinger state. So a very weakly squeezed state is a so-called Schrödinger kitten, how it is sometimes called by opticians. So essentially, yes, the answer on your question is yes.
Kirill, I have one question myself. When in the future we are going to create a distributed quantum computing, as you are trying to do now in Munich with connecting with the cold link to Kreisstads. So there are two approaches: sending individual photons and doing this with continuum variable. And what is your perspective? Which one, in your view, is promising or better, or is it obvious? Is there an obvious answer?
I honestly we are thinking about these differences for quite already some time, because I'm very well aware of many other remote entanglement protocols which can be implemented with single photons. Obviously, something Andreas Wallraff is doing, or Cleland is doing in the US, and some other people all over the world. And this is definitely a good alternative path. One of the advantages of a continuous variable, which is known from general quantum opticians and not so well known in our community, is that in continuous variable, you can really use more effectively the so-called quantum capacity of your channel. It means that you can generate more entanglement, and as a result, you can faster and stronger, better entangle your remote qubits. But since the fact that you always need to convert from one regime to another, you always pay some price when doing this conversion. So what will be the kind of the result, whether this kind of advantage in terms of quantum capacity will kind of outperform the conversion losses in terms of quantum entanglement? This is not clear to me. This is why I'm very interested in those remote qubit entanglement experiments, and hopefully we will be able to do some experiments in the next few years. It's a very important and interesting question, but I don't have a good answer at the moment. I would like to study it.
Okay, so we're already a little bit beyond our time scale. Kirill, thanks a lot for your nice overview and a very didactic lecture, and also showing the latest results. I think it's a very nice perspective which people could grasp. And there are several thanks in the chat, including a thank from your former advisor in Nizhny Novgorod.
Yeah, I see. Yeah. Thank you too. Thank you too for your attention.
Okay, thank you. Bye-bye.
Ciao.